Hello, class. Mr. Bean here, and I've been asked my few students here to perhaps review the elevator and give some hints on the elevator simulation. So we'll go ahead and kind of take a look at that right now and kind of see what we got going on here. Alrighty. So the elevator. Now, before we start the problem here, let's talk about what's called the normal force and weight. So let's take a look at that right now, and let's go ahead and kind of draw like a surface here, and we have here a person standing here, like so. Okay, and oh boy. Okay. All right, so we're here, and so the person is not accelerating downwards or upwards, so we're only considering the forces in the vertical direction. And for purposes of this argument here, we'll say going up is positive, going down will be negative. Okay? So up here we have positive and negative. So so what happens is we're going to assume that all the forces are concentrated right here, let's say, at this point here. So if I draw the point over here, I have going up will be what's called the normal force. And that'll be what we call the force here, normal. And let's kind of make it a little nicer here. This will be the force normal. And acting downward with the same magnitude, just opposite direction, will be what we call weight. Okay? And weight, of course, is going to be the force of gravity. Draw a little g here. And it is simply just mg, a person's mass times the local acceleration due to gravity. In this case, on the Earth, it's 9.8. So up here, we know that the magnitude of g, is going to be, we'll say here, 9.8, right here, right? Meters per second squared. I'm going to try a different mouse here, see if that makes any difference here. Okay, so over here we have the normal force, and over here we have weight. So these are all balanced here, and we can see here you're not accelerating. So it looks like there's no acceleration. So we'll go ahead and put an A here, and the acceleration here is zero, and because you're not accelerating up or down. So over here, we'll go ahead and go sum of the forces um, is equal to ma, like so. Okay. So on the left side, what are the forces acting? Here is these forces up here. So we have the normal force, which is positive. We'll go ahead and put here, force normal, like so, minus the force of gravity. Okay. And so remember now it's negative here, right? It's negative. So, negative 9.8, that's negative, equals zero because acceleration is zero. Therefore, in this particular case, the normal force is equal to just mg. Okay. So the normal force in this case is just equal to the weight, mg. Okay. Now, what does this imply? Okay. This implies zero acceleration. Okay. There's no acceleration. It also implies that velocity is either zero, so a person's at rest, or they're moving with constant velocity. Constant velocity. We'll say constant. Okay. Con, uh, Constant velocity. Okay, so that's kind of a little overview of normal force and weight. Again, normal force is just the floor pushing up against a person with the same magnitude, just opposite direction of weight. All right, now here's the elevator problem, the three different scenarios here. Okay, this one here we already kind of talked about. So scenario one, so this is scenario one right here, scenario one. Okay. Let's take a look at scenario two. So going up is going to be positive, going down is negative. Okay, and it says here greater than normal weight. Why is that? So let's see why that is. So here we have some of the forces. Right? Some of the forces is equal to ma. Okay. So in this particular case, acceleration is going to be positive. Okay. Now, if you want to, you can say that acceleration has a value of, let's say, 1 meter per second squared. 1 meter per second squared, like so. Okay. So, So over here, we do some of the forces. Okay, so we have the normal force acting upward. So here's the normal force, minus mg, right? Minus mg equals ma. Okay, so here the normal force, which is the scale reading. Okay, what is the scale going to read? The normal force is equal to. So here we have ma, right, plus mg. Okay, and we can do some distributive property backwards. We're going to go ahead and factor out the mass here. Okay, that should always be the same. And here we have acceleration a plus g. Okay, so if acceleration is 0, then it's just mg. But because we're accelerating upwards, the normal force is going to read heavier than it would at rest because you have a plus g. So it makes the normal force a little bit greater. Okay. Now, back over here, I forgot to mention, if I wanted to find mass, the person's mass right here, right? So to find the person's mass, you find out their weight at rest. Okay. So it's going to be the force of gravity, okay, whatever the force of gravity is, or their weight divided by g. Okay, so that could, again, or that could be the person's weight at rest divided by g, and that will get you your mass. Okay. All right, so here we go. So when you're accelerating upwards, you have an additive effect. So there's a greater acceleration, therefore you're heavier. Now going down, here we have acceleration is negative, right? Acceleration is negative. So going through the whole thing here again, so we'll go ahead and go to this part right here. So the normal force minus mg, right, is equal to ma. Now, except this time, acceleration is negative. So we have to put a little negative sign out here. Negative, right? Negative. So now when I do this, we have here the normal force is right here. There's the normal force. It's going to equal, now this time you're going to be careful, this mg minus ma, like so. Okay, so now the normal force, right? Okay, now this is going down. So maybe we can say normal force, we'll put a little d here going down. And maybe up here, normal force going up, going up. Okay, so normal force going down is going to be, factor out the m. So there's the m here, right? And now this time, got to do parenthesis here, g, the acceleration due to gravity, is going to be subtracted out from the acceleration, like this. So the effective g now is less. Therefore, the person would feel lighter going down while you're accelerating. Okay? Heavier in this case, lighter in this case. Now over here, this is a free fall situation. A equals g. Okay? And you're falling downwards. Okay, so they're equal to each other. Okay, 0. Okay, okay. Weight is 0. Let's figure out why that is. So here we have again the normal force here. Okay, there's the normal force minus mg, right? Okay, equals, okay, and g is equal to a, so we can go ahead and maybe just put minus ma here. Okay. They're equal to each other. Okay, they're equal to each other, so these could both be positive or both be negative. So when I look at this, or actually, let's go ahead and substitute in the values here. So here we have Fn, right, minus mg equals minus mg. So they're the same, right? So that means here that the normal force is now going to equal 0. Doesn't mean there's no gravity, it just means it's been countered or it's been canceled out temporarily. So the normal force is 0, therefore you are weightless. Okay. All right, now, with that said, let's take a look at this elevator simulation problem. So let me come up here and let's take a look at it and kind of see what we got going on here. And see, we're loading some things up here. I don't need this here. Okay, so let's go ahead and come on down. Okay, let's come slow. Here we go. Elevator. simulation, right? There we go. Take a look at it. Okay, so what we have here is you have access to a very tall building with a variable power elevator, and there's a scale on it here, and you can either go up or down. It's going to give you a force versus time graph from which you have to determine several different things about it. Okay. So go ahead and click on the problem here, and I'm going to go ahead and just click up. Okay, we're going to go up here, and we'll see what happens here. So we're going to go up, and we'll hit start. Okay, so here we have Bart Simpson. He's going up the elevator. Okay, now remember, now it's accelerating. Think about your elevator experience in the elevator at Carson High. All right, so we go here and we go to graph. Now down here is the graph, and now there are some distinct regions that we want to take a look at. So let me go over here and mark with a pin here. Okay, so we're going to call this here, this region right here, we're going to call this region 1. Change pins here. This will be region 1. Okay, this part right here we will call region 2, just to kind of help us out a little bit. This is region 3. Okay, here's region 3, and here's region 4. Okay. And then finally, here's region 5. So physically, what is going on here? Okay, so this is I'm going to go ahead and put down here. I'm going to say rest. This is you're at rest here. Let me make this kind of nice here. Okay, so you're at rest. Okay, you're getting on the elevator. You're at rest. Okay, so if I'm at rest, that implies that the acceleration here is 0. Okay, this part here, we're accelerating upward. Okay, so acceleration here is going to have a positive value because we are accelerating upwards here. Okay, just keep that in mind. Right? Here, once we have reached, and then while we're accelerating, it's going to stop accelerating. So there is some final velocity here. There's some final velocity. We'll put VF here, some final velocity. Here, we're at constant motion. Okay, now look at the acceleration. It's at the same level here. Okay, so here the acceleration is 0, no acceleration. Okay, and we're moving with constant motion. So velocity here then is going to be constant. It's going to be constant. We're going to write down here C, constant, constant. Okay. In fact, whatever this velocity was here is going to be this velocity here. Okay. So, right, so zero velocity. Now here, notice here the person's force scale dropped. So we're decelerating, okay? So that means here the acceleration here is going to be negative. Okay, acceleration is negative here. Okay? Now we're still going up, but acceleration is now in the opposite direction. Okay? We're now slowing down. Okay, we're slowing down. Okay, and when we're slowing down, there might be a new velocity here as well. Okay, well, eventually the final velocity is going to be, so whatever this velocity was here is going to be the velocity here initially, and then the velocity here is going to be 0. Okay, it's going to come to rest. Velocity is going to be the final. Let's say the final velocity. Make a look at the velocity here is going to be 0. Now in this region here, acceleration is also 0, and we are coming to rest. So we're at the top, we're on the top floor. Okay, so the question is asking us, how far did we actually travel, and what's the top speed reached? Okay, so here there's no movement. So here we're going to have, let's go ahead and call this region. Okay, we're going to call this Y1. Okay, this will be Y1. This here is going to travel, so it's moving here, and it's moving here. This will be Y2, right? This will be Y2. Okay. And right here, it's slowing down, but it's still moving as well. And then finally here, we reach our top floor. Okay. So let's take a quick look here and see what Y1 is going to be. me kind of draw it over here. So y1, the first distance traveled here, okay, let's go ahead and go here. Okay, it's going to be v velocity in the y direction initially, right, times time, because we're given time here. Time is down here. Now, it's accelerating, right? It's accelerating. So we're going to go here and go plus, we'll go here 1/2, right? 1/2, was it a t squared. Okay, so this is our first equation we're going to have to use here, right? And the also it's going to ask us our final velocity. So the final velocity here, or the top velocity here, is going to be v is equal to v o y, right, plus a t. That will take into account for our top velocity. So people are asking, well, what about the g here? You know, where's g? Well, g is still there, gravity, but we're talking about the elevator accelerating. Okay. Now, also I forgot from right here. So when we're at rest here, we have to figure out there's the normal force here, right? I figure out the mass, the person's mass. Here's the normal force. That's going to equal, right, mg. Okay, right, mg. Okay. So there's mg here. So to figure out the mass is whatever this weight is here. So it's going to be, so the person's mass is going to be, right, here is Fn, right, here's Fn here, divided by, we'll say here, g, acceleration due to gravity. And I think you're on the Earth here, okay, so that's mass. Okay. So this is what you need to do in this region here. Okay. Now, y2, yeah, let's take a look at y2 here. Let's go ahead and slide it down here. Okay, so y2, here is y2. So in the second region here, right, so we're going to have here VOY, okay, again, right, times t plus 1/2, right, at squared. Okay, all right, now, a couple of things here. What's the acceleration here? It's 0. So this whole term is gone. We don't have to worry about that. Now, what's the initial velocity? Well, whatever the final speed here is the velocity here, is the initial velocity here. So that needs to go here. So whatever this velocity is, final, is the velocity here, and that needs to go here. And that's the distance traveled. Y2 is this velocity times the time interval in this part right here. Now here, we're accelerating or decelerating, so the force is less, and we have to kind of figure out what the acceleration is here. Okay, what is the acceleration? Okay, so what we have to do over here then is go ahead and take a look. Here is going to be, okay, so whatever this velocity is here, so final velocity here is a velocity here is the initial velocity here. So it's going to be VOY here, right? So VOY, right? Times the time interval. But this time we're going to go minus 1/2 AT squared. A t squared. Okay. Now, question is, how do we find A? Okay. Valid question. How do we find A? Okay. Well, it's the elevator problem. So to find A, we're going to have here, here's the normal force right here, right? We'll use this equation right here. Equals, right? So there's a person's mass. Okay. There's a person's mass right here. And here we're going to have G, whatever G is of the planet. There's G, right? And now make sure this is positive. A lot of people were putting negative in there and some other things. Okay, is positive. So what you need to do to figure out A, okay, you have to read the graph. Okay, you know, wherever the force is over here, you know, this will be your normal force. That will go here. The person's mass will not change. G will not change. You got to calculate A going up and then calculate A going down. So whatever A value you calculate here will go here, and when you go down, the other A value will go here. And now when you do it, this will be, I mean, it's negative here because this is going to be negative when you're going down. Therefore, that's why I have a negative here. Over here is positive. Because of what this is, this will be positive. All right, so go and give that a shot here, and any questions, let me know.